So let's apply principal component analysis to the iris data set. This is a 4-dimensional data set that we're going to reduce down to 2 dimensions, and we're going to see that we can actually still preserve most of the information in that data set, even by throwing away half the dimensions. It's pretty cool stuff, and it's pretty simple too. So let's dive in. All right, let's do some principal component analysis and cure the curse of dimensionality. So it's actually very easy to do using scikit-learn, as usual. And again, PCA is a dimensionality reduction technique. It sounds very science fiction-y, all this talk of higher dimensions, but just to make it more concrete and real again, a common application is image compression. So you can think of a black and white photograph, an image of a black and white picture, as 3 dimensions, where you have width, your x and your y axis of height, and then each individual cell has some brightness value on a scale of 0 to 1 that is black to white or some value in between. So that would be 3-dimensional data. We have 2 spatial dimensions and then a brightness and intensity dimension on top of that. If you were to distill that down to say 2 dimensions alone, that would be a compressed image. And if you were to do that in a technique that preserved the variance in that image as well as possible, you could still reconstruct the image without a whole lot of loss in theory. So that's dimensionality reduction, distilled down to a practical example. Now we're going to use a different example here using the iris data set. And scikit-learn includes this. All it is a data set of various iris flower measurements and the species classification for each iris in that data set. And it has also, like I said before, the length and width measurement of both the petal and the sepal for each iris specimen. So between the length and width of the petal and the length and width of the sepal, we have 4 dimensions of feature data, of information in our data set, and we want to distill that down to something we can actually look at and understand, because your mind doesn't deal with 4 dimensions very well, but you can look at 2 dimensions on a piece of paper pretty easily. So let's go ahead and load that up here. There is a handy-dandy load iris function built into scikit-learn that will just load that up for you with no additional work, so you can just focus on the interesting part. And if we take a look at what that data set looks like, you can see that we are extracting the shape of that data set, which means how many data points we have in it, 150, and how many features or how many dimensions that data set has, and that is 4. So we have 150 iris specimens in our data set with 4 dimensions of information. Again, that is the length and width of the sepal and the length and width of the petal, for a total of 4 features, which we can think of as 4 dimensions. And we can also print out the list of target names in this data set, which are the classifications. And we can see that each iris belongs to one of 3 different species, Setosa, Versicolor, or Virginica. So that's the data that we're working with. 150 iris specimens classified into one of 3 species, and we have 4 features associated with each iris, being the length and width of the petal and the length and width of the sepal. So let's look at how easy PCA is. Even though it's a very complicated technique under the hood, doing it is just a few lines of code. So we're going to assign the entire iris data set and we're going to call it X. We will then create a PCA model and we're going to say n components equals 2. So we want 2 dimensions. We're going to go from 4 to 2. We're going to use whiten equals true. That means that we're going to normalize all of the data and make sure that everything is nice and comparable. Normally you will want to do that to get good results. And then we will fit the PCA model to our iris data set X. And then we can use that model then to transform that data set down to 2 dimensions. And let's go ahead and do that. Happened pretty quickly. So think about what just happened there. We actually created a PCA model to reduce 4 dimensions down to 2, and it did that by choosing 2 4-dimensional vectors to create hyperplanes around to project that 4-dimensional data down to 2 dimensions. And you can actually see what those 4-dimensional vectors are, those eigenvectors, by printing out the actual components of PCA. So PCA stands for Principal Component Analysis. Those principal components are the eigenvectors that we chose to define our planes about. Okay? And you can actually look at those values here. It's not going to mean a lot to you because you can't really picture 4 dimensions anyway, but just so you can see that it's actually doing something with principal components. So let's evaluate our results. The PCA model gives us back something called the explained variance ratio, and basically that tells you how much of the variance in the original 4-dimensional data was preserved as I reduced it down to 2 dimensions. So let's go ahead and take a look at that. What it gives you back is actually a list of 2 items for the 2 dimensions that we preserved. So this is telling me that in the first dimension, I can actually preserve 92% of the variance in the data. And the second dimension only gave me an additional 5% of variance. And if I sum it together, these 2 dimensions that I projected my data down into still preserved over 97% of the variance in the source data. So 4 dimensions weren't really necessary to capture all the information in this data set, which is pretty interesting. It's pretty cool stuff. So if you think about it, why do you think that might be? Well, maybe the overall size of the flower has some relationship to the species that it's in, or maybe it's the ratio of length to width for the petal and the sepal. You know, some of these things probably move together in concert with each other for a given species or for a given overall size of a flower. So perhaps there are relationships between these 4 dimensions that PCA is extracting on its own. It's pretty cool and pretty powerful stuff. Let's go ahead and visualize this. So the whole point of reducing this down to 2 dimensions was that's so we could make a nice little 2D scatter plot of it. At least that's our objective for this little example here. So we're going to do a little bit of matplotlib magic here to do that. There is some sort of fancy stuff going on here that I should at least mention. So what we're going to do is create a list of colors, red, green, and blue. We're going to create a list of target IDs, so the values 0, 1, and 2 that map to the different iris species, the 3 different species that we have. And what we're going to do is zip all this up with the actual names of each species. So this little line here for IC label in zip target IDs, colors, iris, target names means that we will iterate through the 3 different iris species. And as we go, we're going to have both the index for that species, a color associated with it, and the actual human readable label name for that species. So we'll take one species at a time and plot it on our scatter plot just for that species with a given color and the given label. We'll then add in our legend and show the results, and this is what we end up with. So that is our 4-dimensional iris data projected down to 2 dimensions. Pretty interesting stuff. You can see it still clusters together pretty nicely. You know, you have all the Virginigas sitting together over here, all the versicolors sitting in the middle, and the Setosis way off on the side here. And it's really hard to kind of imagine what these actual values represent, but the important point is we've projected 4D data down to 2D, and in such a way that we still preserve the variance and we can still see clear delineations between these 3 species. A little bit of intermingling going on in there. It's not perfect, you know, but by and large, it was pretty effective. So if you want to play with this a little bit, as you recall from the explained variance ratios, we actually captured most of the variance in a single dimension. You know, maybe the overall size of the flower is all that really matters in classifying it. And you could specify that with one feature. So go ahead and modify the results if you are feeling up to it. See if you can get away with 2 dimensions, or 1 dimension instead of 2. So go change that n components to 1 and see what kind of variance ratio you get. What happens? Does it make sense? So play around with it, get some familiarity with it, and that is dimensionality reduction, principal component analysis, and singular value decomposition all in action. Very, very fancy terms, and you know, to be fair, it is some pretty fancy math under the hood, but as you can see, it's a very powerful technique, and with scikit-learn, it's not hard to apply. So keep that in your tool chest. So there you have it, a 4-dimensional data set of flower information boiled down to 2 dimensions that we can both easily visualize and also still see clear delineations between the classifications that we're interested in. So PCA works really well in this example. And again, it's a useful tool for things like compression or feature extraction or facial recognition as well. So keep that in your toolbox. Know it's there for you.